in day 4. Okay, correction, day 3, right? So thank you so much for joining in. And in today's session, we are going to, yesterday we have understood a little bit about what is hashing and how you can, convert a number from a decimal system to octal, and from octal, okay, so people can convert a number from a decimal system to octal, and from octal, okay, so I request people to mute them. Yeah, so sorry. So people who are watching us on YouTube, thank you for joining us. And people who are watching us on Zoom, I request you to mute any one of these channels, right? Thank you so much for joining in. Thanks, Rahul. Thanks, Vijay. We have a lot of people who are joining us from our social channels. Thank you, Vijay Tham. Thank you, Sushmita. Thank you, Sujit. Great. So let's begin. Yesterday, we have learned about hashing. We have understood how each transaction is hashed, and we have learned about different tools to convert from one decimal point to other decimal, one system of numbers to other system of numbers. And later, we've also understood what is a compression function and how you can compress a larger message into just a 256-bit and also encrypt it while you are doing it, right? So thank you so much for joining in yet for another session. So today now we are going to cover a little bit more about the encryption and the cryptographic functions, right? So I'm going to share my screen here. Now, if you're able to see my screen, you can see that today we will understand what is the need for public key cryptography, right? So basically, now we understand what is the difference between private key and public key, right? So what happens in a private key cryptography is, for example, if I send a message to a person, say Prem, what happens here is the same secret is used at both places, encryption and decryption. For example, if I have a secret key and if the other person knows it, what happens is they'll be able to decrypt it, right? But what happens in public key cryptography is there are like two keys. Like when you go to a bank, you have to have, for a locker to open, you need two keys, one from there and one from your end. So here the thing is both keys are with you. One is like a public key and another is a secret key, right? So we'll understand a little bit more about it. So this private key is used in regular cryptography, but if you want to encrypt something complex, you'll go for public key cryptography. And what it does is it encrypts a plain text, and to encrypt that particular plain text, a private key is used, which is only available to that person. And when you use a private key, cipher text gets generated. So basically what happens is, if I want to send a message, I don't send a message, I send a little encrypted cipher, right? Whatever message is there, now it becomes encrypted. We'll see it in a visual format. It becomes a cipher text, and then that cipher text gets decrypted by using the private key of the sender, right? So let us understand this with an example. Now, every user has a pair of keys. One is a public key and a secret key, and the key has to be top secret, like it has to be yours only. You cannot share it with others. If you share it, then all of your data will be visible for everyone, right? So the security is lost. So it is very important that the secret key that you have stays along with you. Only you on the earth should know, right? The encryption and decryption process using public and secret key, we will just understand. So for example, if A wants to send a message to B, how it works is A has a public key and A has a secret key. B has his own public key and a secret key. So first what A does is, if at all B is trying to send a message, we use the public key of A and encrypt. We use the encryption function and encrypt by using the public key of A and the message. So how do we get the public key? We get it because it is public. You can ask the other person, can I have your public key? And you use that public key and your own message. The message is that you want to share, right, secretly. You use that and use the encryption function to generate a ciphertext. Now you use the ciphertext to later on decrypt and get your message back, right? So this is what how your two keys get involved, the public key and the secret key, right? So basically what happens is, if B is sending a message to A, B will obtain the public key of A, and then he will run the encryption algorithm. He'll generate C, and then B sends C to A, right? So for example, if somebody is eavesdropping on this line, right, and trying to understand what B is trying to send A, he will know that he sent C, but he cannot do anything with C. Any eavesdropper or anybody who is trying to understand the message in between of two people, he'll not understand because it's a ciphertext, and that is only decrypted by A's secret, right? So though he will get the message, he'll not be able to decrypt it. So that is what is the security that is promised by this particular system, right? So we understand how a message can be securely sent, and how an eavesdropper will not be able to decrypt a message because he does not have a secret key. And we also understood the importance of this encryption function, because this encryption function is only one-way function. For example, what we mean by one-way function is, you can encrypt whatever message it is there, the whatever ciphertext is generated will not be easily able to decrypt it, because that algorithm without the secret key is very tough, right? It is not feasible for anybody to decrypt it back. So that is that is the reason it is called only one-way function. All of the encryption functions, the first step functions, are one-way functions, and this maintains the security, right? So I hope that clarifies this particular topic. Now, if at all we need to understand a little further, any particular agreement between two people happens via a digital signature. So what is a digital signature? Like any signature between two people. For example, if I am taking a property on lease, the rental agreement is something that we agree on, right? So, and we physically sign it. Similarly, on online world also we use digital signature, but how do we make it in a way that if, for example, I agreed so and so rent has to be there, the other person should not be able to change the rent later and say that this person agreed, right? So it should not be editable. The agreement should not be editable. And I cannot deny saying ki, no, if let's just say I agreed for 10,000 and I say, no, I agreed for 8,000 only, right? Two ways. We have to protect the person who is agreeing, who is making the agreement, and who is signing the agreement, right? So how do we do that? We use digital signatures here, and digital signatures employ both these encryption decryption algorithms, right? So we understand how this happens. The public key and secret key are used in the signing process, and digital signature is the thing that binds the association between two people, right? Based on the agreement. So the key properties of the document include unforgeable, meaning the person should not be able to change it, and it should also be not deniable, right? I should not be able to deny it. So how do we do that? Here we understand this in a little bit. This also helps if you attended our yesterday's session where we understood the SHA-256 or hashing, right? So now what happens in digital signatures is, first, if I am signing an agreement, for example, the message or the agreement is M, and we'll run it through this signing process. And here, while signing, I'll be using my secret key. And because of using the secret key, the cipher gets generated. And what is generated here is the agreement. Now, what happens is, if somebody wants to verify if the signature is by so and so person called Sachi, what they do is they'll run it in a verification function, and they'll pass in the agreement that is generated using the signing function. And with that, they'll also encrypt the message, and they'll check if this is properly signed by uh, A. But here they do not need the secret key of A. They'll just be able to verify it with using A's public key. So now what happens is anyone can sign an agreement, and the agreement gets generated, and anybody, so only the person who has digital signature can sign it, but anybody can verify it, right? If like the Aadhaar card could be yours, it could open based upon your fingerprint only a few places, but anybody else can verify if the Aadhaar card is valid or not, right? So that is how this works. Now, but what happens is many times the uh, message, the agreement that we want to encrypt using the signature function is many times very large. It's not like a small two-liner agreement, right? So these functions, if it's a bigger agreement, or sometimes a document could be a video or a media document which goes into MBs or GBs. So the challenge here is becomes very large. So that is the reason we use hash functions. Yesterday we have learned about hash functions. What hash does is it compresses the actual message or the document and generates a fixed length bit string, and this is unique to every input, right? Whatever input is given is very unique. So no two signatures, the hash of any two signatures could be same, right? So everything will be unique. So that is how we do it. So we'll try to understand this here. Now, a signing algorithm takes a message and a secret key produces a signature called sigma, and a verification algorithm takes the signature and the public key and can be executed by any third party to verify the authenticity of the signature. The mechanism of the digital signature provides both the unforgeability and non-repudiation. Repudiation meaning that a person says, no, he can deny. Non-repudiation means that he'll not be able to deny, because the verification says that, yes, this is signed by actual that person only, because it has his own secret key, and the verification will tell that, yes, this is the right signature or wrong, right? So it protects both the parties. The signing algorithm can only be executed by the signer, while the verification algorithm can be done by anyone, right? So this is the concept, right? Now here, if you understood till now, you understood the concept properly. But now if you want to dive in a little deeper on how this security is there, we'll go into a little technicalities here. Now, how do we determine, here we are doing a little geometry, let's say. What happens is whenever there is a point that is there on any particular line, what happens here is, if the point is on a line, if it satisfies the equation of the line, right? We know that the 10 comma 35 is a point that is on this line y equal to 3x plus 5 if you substitute 10 in term at x. So 30 plus 5 becomes y is 35, 10 comma 35 is on this line. So now what we are going to do is we are going to learn something about this very unique curve called elliptic curve, right? And any elliptic curve follows a equation format, which is y square equal to x cube plus ax plus b. And in that, if at all you see, there is a special case where ax, here a is 0 and b is 7. So y square equal to x cube plus 7 is a specific elliptic curve. It looks in this kind of layout. What this does is, this particular y square equal to x cube plus 7 curve is the elliptic curve that satisfies this equation. Like any point that satisfies this equation has a special property, right? So we'll try to understand. So this particular equation provides us a few security features, and how do we use this for our securing our algorithms? We'll understand that also. So any non-vertical line, a few properties of this curve is any non-vertical line that intersects at two distinct points, right, will also intersect at exactly one more point with the coordinates x comma minus y, right? So basically, for example, if a line is intersecting at this particular point, it will also intersect on the other side of that particular line as well, which will be x comma minus y, right? So we'll understand this by an example. So this is one property, that there is xy and x comma y on this particular curve. There is also one more property that is called point addition. Means if you know one point, you can create the second point on that particular curve by using this operation called point addition. We'll understand about that, right? So now if you see this curve, y square equal to a x cube plus bx plus c, if a is 1, b is 0 and c is 7, you will get this y square equal to x cube plus 7. Now y square equal to x cube plus 7 mod p. Mod here is nothing but the remainder, right? So you can definitely we'll do this with an exercise, so it will be helpful. Now the point at infinity, meaning the point at the 0 comma 0, wherever you reach, the point at infinity is denoted at 0 comma 0. So here the point at infinity 0 comma 0 is identity element for point addition, meaning any point above and below will be identical. The curve has a symmetry about y x-axis, because you can see that around x-axis it is symmetrical, and these properties make the elliptic curves particularly useful in cryptography, and specifically in the elliptic curve digital signature algorithm, right? And we'll understand a little bit more about it. So let's just say we have the curve y square equal to x cube plus ax plus b. Now in this, let's try to see if one particular point is satisfying this equation or not. Let's just say we have this question is, does 7 comma 6 belong on the curve? Now what we are going to do here is we are going to check if it is belonging. So we'll check substitute 7 in terms of x cube, and y should be whatever the values there on the right hand side. But now when we do that, we can see that x cube, which is 7 cube, is 7 into 7. You can use a calculator here. 7 into 7 is 49, and 49 into 7 is 343. So the 343 plus 7 is 350. But now 6 square is 36. So now 36 mod 11, meaning the remainder when we divide 350 by 11 is 9, but 36 mod 11, meaning when you divide 36 by 11, the remainder is 3. So both of these are not equal, and that is the reason this particular point does not belong on the curve. Now that is how you check. But the other point addition, for example, you have one point, you want to identify the other point, you can just go ahead and do p. If you have point p, then you can do p plus p, you will get 2p, and similarly you can add and get all the points that are there. And there is another way also. There's another way called scalar multiplication. If you multiply any point with a specific numeric, that is called a scalar value. When you multiply a scalar value with a point, then it will be called the scalar multiplication, right? So you'll understand these in a better fashion here. So if at all you want to, I do not want to manually do this p plus p plus p plus and all, and you want to identify the other points based upon a formula. Like for example, if P is x1 y1 and 2P is x2 y2, you want to do this particular equation, there is a way to do that. So how do you do that is there's an equation which is a shorthand. You can remember it, or you can keep a note of it, that there is a formula, but there are better ways to even identify this. There is a formula which says lambda, which is the slope of the line, equal to 3x1 square plus a into into 2y1 inverse, basically, by, which is 1 by 2y1 mod p, right? So this is how this equation goes. And we'll understand a little more important properties of how now we understood the curve, but how does this curve provide the security? That is the most important thing, right? So now we need to understand that for a user to participate in a blockchain, Bitcoin blockchain, they must have a secret key and a corresponding public key. Now, in our lectures, we have also mentioned that the secret key is a 256-bit number, and the public key is generated by multiplying the secret with a generator point on the elliptic curve, right? So this we will be able to show it on a graph, so it becomes easy for you to understand. Now what happens is, if at all you have a secret key which is a 256-bit number, you can get the public key by multiplying the secret key with something called the generator point on the elliptic curve, right? So if the secret key is 256-bit, the public key is 512 bits in size, because now you can see that here in the equation, x, if you have one particular x1, the other y1 will also be 256. So now two 256 bit numbers will give you an output of like this 512-bit sized public key. Now the public key P is equal to x1 y1, and if x is the secret key, then y will be the public key that will be generated by the generator point on the elliptic curve. So that is how the elliptic curve becomes very useful, to know what is the public secret key based upon the public key. And this is done with specific software that is getting generated. So you need not have to give both public key and secret key at once, right? So the encryption function by itself will be able to verify based on the elliptic curve, because if you give secret key, it will be able to match it and check, okay, yes, now that this particular input has come, if I multiply with a generator point on the elliptic curve, I'm going to get public key. And if based upon this was the public key given, and if while verifying, it sees that the match is happening because it multiplied it with the generator point, then it says, yes, this is a valid signature or valid document, right? So the algorithm uses the elliptic curves properties to generate and know what is the secret key based upon what is the public key, and validate. It will not give out the output as a secret key, but it will validate if this is the right secret or not, right? So now that is what is the elliptic property and how it helps in digital signatures. And tomorrow we'll be understanding a little bit more about wallets, and we'll be doing a little practical exercise to understand how wallets are useful, right? So I hope this session was valuable. And if you are joining us on our social channels, you can leave your top learnings in the comment section. And as we join every day for 30 minutes, we will be joining on the 7th day, where in our masterclass, we'll be giving you more details on how you can launch yourself into this blockchain career and learn from the basics in a better manner as well, right? So the link to the day 7 session will be shared in our progressive tomorrow's and day after tomorrow's session. But thank you so much for joining in. Thanks, Vijay. Thanks, Prashant. Thanks, Sujit. Thanks, Priyanka. Thanks, Sham. Thanks, Raja. Thanks, everyone, for joining in. And thank you, Priya. I hope this was a very valuable session for you. If at all there was any confusion, we'll be taking the questions in our next session. So you can make your wise by watching the same video on YouTube. And if there's any challenge, you can reach out to us in our next session. Looking forward, and thank you so much for joining us.